Hello, my name is Ben Fulp, and today I'll be presenting to you about stars and star life. A star is fundamentally a giant sphere of gas, mostly made of hydrogen and helium, that fuses hydrogen into helium in its core. A star's gravity pushes in on the star, but is counteracted by the pressure created by the star's nuclear fusion in its core. This is called stellar equilibrium. Stars are born in a nebula. A nebula is what remains after a star after it has died, or another star. The reason stars are born here is because nebulas are primarily composed of clouds of gas and dust, such as hydrogen and helium, which is ideal for the creation of a star. In the nebula, a cloud of gas and dust coalesces into a protostar. A protostar is a hot ball of gas and dust which has not yet begun to initiate nuclear fusion at its core. As the temperatures and pressures in the protostar's core grow hotter and hotter, atoms become more violent, and until at 15 million degrees, nuclear fusion begins. A star is born. Most stars in the universe are main sequence stars. Main sequence stars are characterized in three ways. They all have stellar equilibrium, which means that the pressure of the fusion at the center of the star and the gravity pushing in on it are balanced. Another trait of a main sequence star is that it fuses hydrogen into helium in its core, not heavier elements. The picture shown on the slide shows the different types of main sequence stars. This chart classifies stars depending on their luminosity and surface temperature. At the extreme light, the most luminescent and hot stars, the O-class stars, sit. These stars are very rare and will transition into supergiants, which are very, very large stars, and go supernova in the later stages of their life. They live for a very short amount of time due to their luminosity and extreme temperature, only a couple million years, and are not good candidates for life due to their short time span. At the extreme left, we have M-type stars. These are the cooler, less luminous stars. Most of these stars are red dwarfs, but it's important to remember that even though most M-type stars are red dwarfs, red giants and red supergiants, massive, extremely luminous stars, also exist in the M-type. Red dwarfs make up over 70% of all stars in the universe. Despite their overwhelming commonality, you've never seen a red dwarf in the night sky because they are so dim, up to thousands of times less luminescent than the sun, and the sun isn't a very luminescent star. Our closest neighbor is a red dwarf named Proxima Centauri. Red dwarfs live very, very long lives, trillions of years in length. This is because they do not have a typical core at the center of their star, but instead they convect their hydrogen, which means that they take it from the outer layers and they fuse it from the outer layers, unlike a core. Red dwarfs are seen as likely candidates for planets with life due to their long lives and the fact that they often have terrestrial planets around them. As we move well on the scale, we see K-type stars, orange dwarfs, and D-type stars, yellow dwarfs. Our sun is a yellow dwarf. If you're wondering why O-type stars are, more blue and M-type stars are red, it's because blue type stars are hotter than red. So that's just an explanation right there. Our sun is a yellow dwarf. Our sun's sister stars, excluding Proxima Centauri, are also yellow dwarfs. In the middle lie the white F-type stars, the light blue A-type stars, and finally the B-type stars. And B and O-type are among the hottest and most luminescent stars in the universe. They also live the shortest. Every star in the universe will die eventually, but its mass determines how it will die. Most stars are red dwarfs, and red dwarfs go out with a whimper. If a star is less than half the mass of the sun, it will use up its fuel for trillions of years and then turn into a white dwarf. A white dwarf is the remains of the star's core, a white hot object the size of a planet that will slowly cool over trillions and trillions and trillions of years. If a star is 5 times the mass of the sun, it will use up its hydrogen gas, but instead of collapsing, it will begin to use helium as its nuclear fuel, fusing helium into carbon. The star will begin to expand into a red giant, swelling to hundreds of times its original size. Now, it's not getting larger in terms of mass. Its radius is just expanding. That's important to remember. The stars, when they get larger, they actually often expel their matter. So it's important to remember that just because the star looks bigger doesn't mean it actually is bigger. You also become thousands of times more luminous. When the red giant uses up its helium, it will expel its outer layers of gas and dust, and all that will remain is a white dwarf. If a star is more than 5 times the mass of a sun, its death will be spectacular. Like the red giants, it will run out of hydrogen in its core and start fusing heavier elements. Supergiant will not stop at helium, however, due to its mass. Its mass means that it has a heavier core and more pressure at its core. And with more pressure means that it can fuse heavier elements. However, it will fuse helium to carbon, carbon into neon, neon into silicon, and finally, silicon into iron. Iron is nuclear ash, nuclear dead weight, and the star will collect iron at its core until it reaches a critical mass and the star can no longer withstand its gravity and implodes in on itself. The outer layers of the star collapse and then bounce back off the iron core in a supernova explosion. The core of the star, being squeezed together so much by that explosion, becomes either a neutron star or a black hole depending on its mass. The more massive stars, if you get what I mean, will become a black hole, and then the less massive stars will become neutron stars. These two objects will be explained in the next slide. Stars can turn into many things when they die. Normal stars that are less than 5 times the mass of the sun will turn into white dwarfs when they die. White dwarfs are dense, hot remains of a star's core. White dwarfs will slowly lose their heat over trillions and trillions of years, even though they're not producing nuclear fusion anymore. They lose their heat to space, and that's a very inefficient process. So they slowly lose heat over an enormous amount of time. If a star is greater than 5 times the mass of the sun, it will become a neutron star or a black hole. A neutron star is a very, very dense, hot object the size of a city. 1 teaspoon of a neutron star would equal the mass of the Himalayas, which is just insane. I'm not going to go into the properties of this neutron star because that would take like an hour. There's so much information of how unbelievably extreme it is. It also has an incredible surface gravity, not as much as a black hole, because it hasn't completely collapsed. The core isn't completely, caved in, but still, incredible surface gravity, temperature, and density. A black hole is an extremely massive object that at its center has a point of infinite density, which means no volume and infinite mass. Its gravity is so strong that it bends light around itself in a black hole, meaning you can see the other side of a black hole. This is also in effect with neutron stars, but we don't need to go into that. Basically, it has a lot of gravity. Also, a black hole, basically, I don't know if I want to go into this right now, because this is kind of theoretical. Well, not really theoretical, but physics. So basically, gravity is simply the molding or bending of space-time. And space-time is everywhere. So with a black hole, unlike usual stars that just bend space, make a little hole, no, not a hole, a depression in space-time, black holes just rip through the surface of it, and nothing can escape a black hole once it's crossed what is called the event horizon, which is the surface of a black hole. Not even light. And that's how strong the gravity is. This is possibly, it for sure is one of the most gravitationally extreme objects in the universe, and probably one of the most interesting. Stars are extreme, interesting, and important, and it's important to know about them.